To tell her to come at 4 p.m. instead of 3 p.m.
Continue.
In the same way, you find that when you go to the enteric brain or the communication in the intestinal, gastrointestinal mucosa, you find that these catecholamines again act as neurotransmitters. They are produced there, they are neurotransmitters. But when they're released by the adrenal medulla, they circulate in blood as hormones, as catecholamines. We also find that the hormones of the posterior pituitary, that is vasopressin or antidiuretic hormone and oxytocin, when we go to some parts of the brain, they are also produced at nerve endings as neurotransmitters, usually inhibitory neurotransmitters. Now this is not going away. As neurotransmitters. And again, in the enteric brain, again, in the gastrointestinal mucosa, they are again produced as neurotransmitters. So you can actually see there's quite a bit in common between the endocrine communication and the neuro communication, such that mechanisms of something like sympathetic and parasympathetic system, autonomic nervous system sometimes uses both. And we shall also find that in some areas, like in the hypothalamus, you may have some organs, like in the hypothalamus, which receive neuro inputs, like vagal inputs, and they respond through chemical messengers. They may receive stretch receptor inputs from vagus nerve in the stomach or in the upper parts of the intestines, and then they secrete chemicals or hormones that go to the that affect absorption in the stomach and intestines, and also the mechanisms of regulating glucose and other substances. So there is a lot that we shall be talking about that is in common between the chemical messengers or the hormonal, or what we would be calling the hormonal or chemical communication. We find it is very much coordinated with the neurotransmission. And in the first part of the semester, we'll be talking about chemical messages. We'll be talking about humoral factors. We'll be talking about hormones that are in circulation. Whereas the second part, we shall talk about the nerve mechanisms or the action potential mechanisms. So I sent you these slides, I sent you the notes so that you can have a look at the chemical messengers, you can look at the endocrine system, endocrine communication, and especially the properties of hormones, the properties of the different hormones that we'll be talking about, what type of substances they are, how they are produced, how they are synthesized, how they are released, and how they are regulated. Again, it is also important to know how they are excreted, how they are finally metabolized and excreted, and what are the factors that affect their levels in circulation and their levels at tissues. That is what actually stimulates their production or their release, and what determines their rate of breakdown, their rate of metabolism, and their rate of excretion, so that you can use these parameters to monitor the levels of these hormones, to monitor the levels in the body and the levels in excretion, in urine or other areas, so that when there is abnormalities of hormone overproduction or hormone overactivity, we have ways of monitoring the levels of those hormones. And if we have to replace hormones where we have deficiencies, we have ways of finding out their levels, analyzing what their levels are in blood, analyzing how much to replace, and also detecting how much we are losing, so that if there's deficiency, is it because of poor synthesis? Is it because of poor transport system of the hormone? Or is it because of over metabolism, over breakdown, too much breakdown and loss of these hormones? We also have interactions between the different hormones. Many hormones are actually regulated by actions of antagonistic hormones, or sometimes even agonists. You find something like growth hormone will have agonist action on insulin. Either it will cause insulin increase, or it will have effects that are just like insulin effect at the cell membrane, and therefore the entry and metabolism of glucose and lipids, usually free fatty acids. So that you find there are many hormones that depend on each other in their production. You find something like the glucocorticoids, or the hormones of the adrenal cortex, will have a lot of effect on other hormones that are not necessarily from the adrenal cortex, that are not necessarily steroids. They will even influence the release of medullary hormones, that is adrenal medulla. And they will also have a lot of what we call permissive action on other hormones. For example, they are major glucocorticoids. And so they will affect how the glucose and other carbohydrate levels and how lipid and amino acid levels are regulated in different tissues in the blood. And this is very important to realize that activities of one chemical or one hormone can be used to regulate other hormones. And therefore, we shall also look at very specific systems from hypothalamus through anterior pituitary to lower glands. And we shall see the hypothalamus has its own secretions that largely affect anterior pituitary hormones, anterior pituitary secretions. And these anterior pituitary secretions are tropic to glands below. They are activating glands below. That is like the thyroid glands, the pancreatic hormones, the adrenocortical hormones, and the gonadal hormones. And you find that this axis from hypothalamus through anterior pituitary to lower glands, and even to tissues like the liver and muscle cells, are very important in regulating body function. So generally, the endocrine system is for regulating and controlling activities of tissues and glands in the body. And we'll be looking at the different systems at different times. And it is important to appreciate the relationship between these different organs, especially the hypothalamic anterior pituitary axis that comes through the thyroid, that comes through adrenal cortex, that comes through the gonads, and even to tissues like the liver and the muscles. So the most important thing about hormonal control or about hormones or endocrine system is a definition, is knowing exactly what we classify as hormones. And we say hormones are chemical messages that convey information, signal relevant for cell function. So they actually give signals. They transport signals to cells, regulating cell function. So they are the ones we mainly refer to as primary messengers, or the first messages to arrive at the cell, normally at the cell membrane. But many times you even get hormones that are produced within the cell having action inside the cell. That is when we'll be talking about whether something is endocrine, paracrine, meaning just next to the cell, paracrine, or even exocrine. Exocrine will be enzymes that are actually synthesized in a cell, and then they are transported out, they go outside the cell to affect tissues or organs nearby. And exocrines are not hormones. That is why we talk about an endocrine system and exocrine system, where exocrine means hormones, or those that are released outside into the outside of the cell. The hormones or endocrine substances are released into the bloodstream. They are released into circulation because they are synthesized in ductless glands, unlike enzymes, and they go to distant organs. They usually have their effect on distant organs, although we said there are some hormones that are exocrine, that are paracrine. That means they affect the cells next to them. Like when we talk about the pancreas, endocrine pancreas, we find that some cells from the B cells, the beta cells that produce insulin, the insulin affects cells next that also produce glucagon, and glucagon acts against insulin release. And glucagon itself is a substance produced by the A cells or the alpha cells of the pancreas, and they have a negative effect on B cells, production of it. They inhibit insulin production. And we can have other endocrine cells in the paracrine cells in the pancreas, that is the delta cells, and which produce somatostatin. And we also have the P cells that produce the pancreatic peptide that is anti-insulin. So as you can see, we have endocrine action that is inside cells. We have paracrine, and we even have what we call the local hormones. Local hormones like histamine, serotonin, or serotonin is 5-HT, 5-hydrotryptophan. And all these hormones can have effect on tissues where they are produced, say like vasoconstriction in small arterioles, a smooth muscle of small arterioles. So we have many mechanisms of endocrine activity or hormonal action. Others are produced by organs that are not necessarily endocrine organs. Like the kidney produces hormones that affect bone marrow activity, that is erythropoietin. And erythropoietin is really the only purely hormone that is produced by the kidney and released. Otherwise, the kidney also has a lot of effect on the calcium metabolism through the vitamin B series, that is the cholecalciferol, calcitriol or to calcitriol production. This happens in the kidney, just like, some steps also happen through the lungs. And finally, their action is on the adrenal cortex and on absorption in the intestinal mucosa, so that the kidneys have an endocrine function to do with calcium metabolism or regulation of calcium by vitamin D hormones, vitamin D series. At the same time, we find that there are other hormones that also go through a process in the kidneys or lungs, like angiotensin. We start with angiotensinogen, we go to angiotensin 1, angiotensin 2, and some of these steps happen either in the kidney or in the lungs, and therefore these organs can also have endocrine function. The heart also does produce ANP, or the natriuretic, the atrionatriuretic hormone, which is a hormone that detects high sodium in the distal convoluted tubules and can increase sodium loss once the high sodium is detected in the muscles of the anterior, in the atrium of the heart, in the atrial muscle of the heart. So that is quite a new hormone, the ANP, or atrionatriuretic hormone. The skin is also very important in endocrine function or transformations of the vitamin D series, cholecalciferol series, so that the process we said from vitamin D2 to D3, the skin has a lot of function in that, using the rays of infrared in the sunlight, and that helps change the vitamin D2 to vitamin D3, or from cholecalciferol, 3-deoxycholecalciferol. The GIT itself is very much involved in regulation of hormones. It secretes its own peptides that regulate factors that regulate hunger, like we saw in the last lecture. That some of these, like the Y peptide and the gluten-sensitive peptides, like the augute alkaloids, they affect the hunger center, they increase feeding, and therefore the mucosa of the gastrointestinal tract is also very useful in hormonal activity. It also secretes many of these hormones that we talked about, like the catecholamines, especially dopamine and adrenaline, and these ones have their own local effect in the gut, especially in gut motility and gut secretions. We have already mentioned local hormones like histamine, serotonin, or 5-HT, and the lipid-based hormones that affect vasoconstriction and that also affect muscle contraction, especially in the uterus. These are the prostaglandins, the prostacyclins, the derivatives of arachidonic acid. These are local hormones. They are produced in the areas where they usually will have their own action. The placenta is also a big source of hormones. Placenta itself, even if it's a hemochoreo that is for blood circulation and oxygen transport, it has an endocrine function. It's itself a big endocrine organ that produces a lot of the steroids, especially progesterone, because placenta largely produces progesterone, but it also produces peptides that are like anterior pituitary hormones. The chorionic gonadotropins are produced by the placenta, especially HCG, and there's many other peptides that are like anterior pituitary peptides. including somatomamotropin, which is both action of growth hormone and prolactin action. And so we find that the placenta is very important, especially for producing steroids and these peptides. So I was talking all that so that you compare the way of release, the action pathways, and excretion of hormones, compare with enzymes, contrast with enzymes, so that when we say hormones are endocrine substances, then we say enzymes are exocrine substances. They are released from cells through ducts to the outside. That is enzymes. Whereas hormones will either be produced into the cell and then they will diffuse through the cell membrane and out, usually through active transport or aided transport by proteins across the cell membrane, or they will have effect in the same cell. So basically, that is hormones as chemical messengers, and with a lot of communication, a lot of interaction with the neuro information system, the neuro affective and effect or response mechanism. So I'm sure we have all looked through the endocrine glands that we'll be talking about. It's very interesting to look at all the endocrine glands from top to bottom and see how their characteristics change. And this is the way you remember them in terms of how they are made and in terms of how they act and in terms of their release. You look at those endocrine glands and you see we have those that are inside the head. That is the ones that are actually part of brain. They are released from cells that are part of brain. That is the hypothalamus and anterior pituitary release of hormones. But even above hypothalamus, there is a small gland called the pineal body, and pineal body produces one basic hormone, a single amino acid hormone, which is called melatonin. Melatonin produced by the pineal body, and it is inhibitory to hypothalamus. It inhibits many factors of hypothalamus, including the gonadotropins before puberty, and that is why you don't get the expression of gonadotropins in childhood, because melatonin is already inhibiting, and inhibits even the adrenal cortex at that time, so that, for example, the lengthening of bones, the growth of bone ends does not occur during childhood, but occurs at a time we will be referring to as adolescence or pubescence. And that is the effect of withdrawal of melatonin when the pineal body involutes or becomes less functional. And that is the only hormone that is above hypothalamus. And as we shall see, it is inhibitory to hypothalamus. It is a single amine, that is melatonin. And we shall compare that with some amines that are also produced by the hypothalamus when we come to that level. And we find something like dopamine is really a hormone that is based on one amino acid. Dopamine, and again, dopamine is inhibitory. Dopamine is largely inhibitory, and it is actually the prolactin inhibiting hormone. So that when we come to anterior pituitary, it will be one of the inhibiting hormones from hypothalamus, and it inhibits prolactin in anterior pituitary, and it is a single amino acid. And even the other inhibitors that are there around that are produced in the hypothalamus will be like TRH, that is a thyroid release hormone That is not inhibitory, it is actually stimulatory, but it is just 3 amino acids. It is a triad of amino acids, which is called the TRH, or thyroid releasing hormone. And next to it is another short peptide, so that we are going from 1 amino acid to 3 amino acids to 10 amino acids. The gonadotropin releasing hormone is 10 amino acids. It's called a decapeptide. So you see a good relationship between these first hormones of hypothalamus with now the hormones of posterior pituitary, because hormones of posterior pituitary come from cells in the hypothalamus along the ventricles in the hypothalamus, that is the optic cells and paraventricular cells around the 3rd ventricle. And these hormones of the posterior pituitary, which are oxytocin and antidiuretic hormone ADH or vasopressin, these are nanopeptides. They have 9 amino acids, so they compare very closely with the gonadotropin release hormone. So that from up coming down, we have seen a hormone of 1 amino acid, we have seen hormones of 3 amino acids, we have seen hormones of 9 amino acids and 10 amino acids. So you can even see in the hierarchy of hormones, there seems to be a relationship between the organs or the areas where hormones are produced and the type of hormone, the size of hormone. We are talking about amino acid-based hormone or simple basic hormones, which brought us from pineal body to hypothalamus and to posterior pituitary. When we come to anterior pituitary, we find totally different type of structures, chemical structures. These are polypeptides. That is the hormones of anterior pituitary, that is growth hormone, prolactin, ACTH, and beta melanocyte stimulating hormone, beta MSH, and even the thyrotropin, the thyroid stimulating hormone or TSH. All these hormones are large amino acids, large peptides. They are polypeptides. They have polypeptides, they have amino acids number about 180. I'd like you to learn growth hormone and prolactin. They have about 192 amino acids, which is very much like insulin. They are very closely related to insulin in their structure. And we shall even see the receptors will have some relationship. And therefore, no wonder growth hormone acts like insulin. Growth hormone has insulin-like activity. It helps insulin to enter, it helps glucose to enter cells. It is anabolic in that it promotes formation of glycogen, storage glycogen from glucose. It helps in polymerization of lipids, so that we have storage fats from free fatty acids, and it helps in peptide formation from amino acids, so that it is growth hormone. It helps, it gives a positive nitrogen balance. It helps to turn small units into large units for storage. It helps in growth. So that growth hormone, even if it's not much of it is produced and not much active in adults, as it is in children and in utero, it has insulin-like activity. It promotes growth. It promotes polymerization of small units to large units. And a lot of times it does not act as the whole growth hormone of 191 amino acids. It acts as pieces, which are called somatomedins. It acts as factors for growth or growth factors, somatomedins. So that we, for example, have somatomedin C or cartilage and fibroblast growth factor. We have bone growth factors, and we have many other growth factors called somatomedins. And indeed, these somatomedins, these growth factors, like they are called IGF-1, that is insulin-like growth factor 1, insulin-like growth factor 3, and things like growth factor C or somatomedin C. These factors are the ones that actually go back to the brain and they inhibit further production of growth hormone. So that when you look at the negative feedback mechanism that suppresses growth hormone production, we'll be thinking about both insulin and insulin-like growth factors, IGFs. So that is anterior pituitary hormones. They are large, about 191, 192 amino acids long, and they are like straight polypeptide chains, but of course they are coiled to save space and not to expose too much of the receptors for activity. The other breed of hormones in the anterior pituitary are what are called the glycopeptides. The ones we've talked about first are straight peptides, are peptides, like growth hormone, prolactin, and ACTH, they are peptides. Then we have the glycopeptides that are produced by adding a glycopart, a glycomoiety to the protein. This increases their reactivity. It also helps in storage and transport. And the glycoproteins are usually made of two subunits, the alpha subunit and beta subunit, where all the alpha subunits are similar and they are produced in the same way. But the specificity and the receptors of the different hormones are on the beta subunit. So we have an alpha subunit, a beta subunit. And these include the gonadotropins, the thyroid stimulating hormone, and sometimes you also see this glycosylation in ACTH. But generally we say ACTH is peptide, but these other two are glycopeptides, that is TSH and gonadotropins. The alpha subunit is about 125 amino acids long. The beta subunit is 81 amino acids long. And these two units are usually bound together by a peptide bond, by a C peptide that connects the alpha and the beta. And even as they circulate, sometimes they are separate, and you can say beta hormone as opposed to the total hormone. You remember, like when you're doing pregnancy test in HCG, and HCG is just like any other gonadotropin, like FSH. And we find that sometimes you do just beta HCG. We don't have to do the whole HCG in blood. We do beta part or beta HCG. And that is where the specificity of the hormone is. That is where the receptors of the hormone bind. Alpha is just like a framework for the hormone, and alpha is the same whether you're talking about thyroid stimulating hormone, FSH, LH, or even insulin. They all have the same alpha. So that was about anterior pituitary hormones. They are mainly straight peptides, long peptides, and the glycopeptides, which are alpha and B complex. And then we come down from there to now the neck glands, mainly the thyroid hormone that produces thyroxine, T3 and T4. The word thyroxine generally refers to T4, that is tetrahydrotyrosine, T4. And most of the thyroxine in circulation or thyroxine that is synthesized is T4. We shall see why later when we look at the synthesis of thyroxine, in that we usually just add iodized to tyrosine. So from monoiodotyrosine, you combine the two and you get iodotyrosine, two iodines, diiodotyrosine. Then when you put two diiodotyrosines together, they make tetraiodotyrosine, they make a T4, so that you don't have T3 on the synthesis system. It is from T1, T2, T4. So that is why most of the thyroxine, when we talk about thyroxine, we mean T4. But the truth is, the active hormone, the hormone that has receptors in the tissues, the hormone that we know is bioactive and bioavailable is T3. So even in tissues or even in circulation, we have to convert T4 to T3 to act. That is triiodotyrosine. So it is important to realize that activity is related to T3 when we come to tissues and target organs. And that is why the process of deiodinization happens in the target tissues. That is where the iodotyronase is. It removes one of the iodo so that tetraiodotyrosine becomes triiodotyrosine, or T4 is converted to T3 by iodinization or the iodotyronase. So we'll see that is important when we come to synthesis of thyroxine, circulation of thyroxine, and finally bioavailability and bioactivity of tyrosine. So it will be important now to understand that most of the thyroxine in the body is made as T4. So over 94% of all the thyroxine in the body is T4. And the active T3 is only 3%. 97% of iodine is of thyroxine is bound, it's not active. Only 3% is active. And that is usually done at the target level. So when we talk about carrying or transport of hormones, we'll be talking about protein carriers. We'll be talking about bound hormone. And thyroxine will be the best example of bound hormone in that over 93% of thyroxine circulates as bound hormone. Only 3% is free hormone or bioactive hormone. We'll find that protein binding is less in some of the other hormones. Like when we come to talk about corticosteroids, like cortisol, their binding is like 50%. When we talk about cortisol, when we talk about testosterone, estrogen, these hormones, these steroids are bound to a level of about 50%. And we'll talk about the binding proteins. The main binding proteins are globulins, but we shall talk about specific globulins and non-specific globulins that actually are protein areas of hormones. And they are very important in that they take the hormone close to the target so that when levels go down, you can easily mobilize or activate a hormone just next to you that is in storage. For example, we have already said the deltoid can be having so much thyroxine, but is T4. And that thyroid may be so active at one given time, like during a marathon or during a sprint, and it finishes all the T3. It doesn't have to wait for more T3 to come from the thyroid gland in the neck. It has a lot of T4 around it. So all what it does, it changes the T4 to T3, and now it has bioactive hormone. And that is the importance of protein binding and the importance of free hormone and bound hormone. In that bound hormone takes the hormone close to the target tissue where it will be used. But we only find the enzyme that will convert it. The converting enzyme, we find it at the tissue. So that is where it does most of the action. Just like you see that testosterone will be circulating over the whole body, but testosterone is not active in many of the organs, in many of the tissues. When it reaches specific target tissues, that testosterone very quickly becomes free. The bound testosterone becomes free if the enzymes are there to separate it from its peptide, from the carrying peptide or carrying globulin. So it is immediately available to its receptors. And that is where the enzymes for breakdown are situated. So as soon as it is bound to the receptor, as soon as it finishes action, it is also metabolized and lost. And this is true of most of the hormones, as you know, just like you have glucose circulating all over the body, but most of the glucose will be metabolized in the liver, and that is where it will find a lot of its receptors. That's where it will be bound highly. Again, in the muscles, a lot of glucose will be released. A lot of glucose will be released at the muscles. And there we even find that even the ATP that normally would be made in the liver using ATP phosphorylase, now here we are going to have a different phosphorylation in the muscles using creatine phosphorylase. Creatine phosphorylase that will make it much faster to release ATP and put more of the phosphate on the ADP that is produced. So regeneration of ATP will be facilitated in muscles, especially during a running race or something. It will be facilitated by myophosphorylase, by creatine myophosphorylase. And this is true in many of the hormones. We find that we have different enzymes in different areas that will release those hormones at the particular place, or that will adjust the hormone so that it is more available to its receptors. It is specific to its receptors. Just like we said, when you have testosterone, although it will act on testosterone receptors across the body, in some organs like skin or other areas, you find it is dihydrotestosterone that will be recognized by the receptor. So that in those areas, say like in the scrotum, in the penis, in the hair bands, like on the face, it is not the testosterone that will be so important for the receptors. It is dihydrotestosterone. And therefore, you have a specific enzyme that reduces testosterone to dihydrotestosterone. And that is called the alpha reductase. You have a testosterone alpha reductase that changes testosterone to dihydrotestosterone, which is what is recognized by the receptors. So when we talk about endocrine system, when you talk about hormones, it is not just levels of hormones in circulation that is important. It is also receptor distribution and receptor sensitivity in the different tissues, so that the same level of hormone can have different actions in different tissues. That is the important thing about understanding this flow of different structures, flow of different types of the same hormone across the different tissues, across the different organs in the body. So that there we were talking about thyroxine. When you look at thyroxine, or the thyroid gland, and the gland below it that is called the adrenal gland, adrenal cortex produces steroids, which are from tyrosine. Tyrosine is a precursor of steroids, just like the same tyrosine is a precursor of the thyroxine, so that those two have the same, has similar structures, have the same precursor molecule. When you come to the adrenal medulla is the one that produces catecholamines, like we have said, adrenaline or adrenaline or epinephrine and dopamine. And these ones also come from tyrosine. Their precursor is also tyrosine. It can be from tryptophan to tyrosine, and then tyrosine now to the catecholamines. So you can see a big relationship between the thyroid hormones, the adrenal medullary hormones. They come from the same type of amine, and they are simple. They are simple structures. And when you look at the adrenal cortex, it's also from simple structure, from tyrosine, that gives us the steroids. No, it's not from tyrosine, sorry, the adrenal cortex, the cortical hormones are from cholesterol. And as you know, cholesterol has two sources. We either have nutritional cholesterol, or we have de novo synthesized cholesterol in the body, which is made from acetoacetate, arise from acetyl-CoA, so that within the cells, within the mitochondria, it is possible to make cholesterol using acetyl-CoA. This cholesterol, which is a 25 carbon structure with a branch at position 21, this is the one that becomes debranched. Cholesterol is debranched by a debranching enzymes or esmolase that puts it, becomes pregnenolone or progesterone. And then now progesterone is the mother of all steroids, the mother of cortisol, corticosterone, the mother of progesterone, the mother of estrogen and testosterone and other androgens. So that as we come down, we have seen thyroxine, we were talking about tyrosine and tryptophan. We have come to the adrenal gland, and we find the adrenal gland, the medulla, we are talking about tyrosine again. The cortex, we are talking about the precursor molecule is cholesterol, and the mother molecule is progesterone. Of course, in between, there's the endocrine pancreas. The endocrine pancreas, again, has something of a relationship with the hormones of anterior pituitary. It's the structures happen to be, and the activities and hormone receptors sharing seems to have something in common with anterior pituitary. And here, the major hormone is insulin. And then after insulin, we have glucagon, we have somatostatin, pancreatic somatostatin, and we have the peptide. We have the P, or the peptide. There's the pancreatic peptide, which is called the P peptide. And all those ones are agonistic to insulin except glucagon. Glucagon is anti-insulin, and somatostatin also inhibits the B cells. It inhibits insulin. But these hormones now look like they have quite a bit of sharing with anterior pituitary hormones. When we come to structure, when we come to the type of receptors, because we'll talk about the main type of receptors that we find in hormone activity. And most of these hormones actually go through recepin receptors. Recepin receptors that have got 7. That's why they are called they're called recepin, because it's like 7. They have 7 receptor sites across outside the cell membrane. And reserpine receptors, the best example, of course, would be the ones for epinephrine, adrenaline, but we find they are very important in the gonadotropin, actions, in thyroid actions, that is in glycopeptides. The other type of receptor is the one that goes through a transcript system, a start system. It may start with adenine structure receptor that then gets through the cell membrane and uses a transcription factor to get to the nucleus. That is the start receptor. So we call this a JAK start system. That is, JAK is guanine adenine kinase receptor, and it alters, or it combines with the hormone and alters it so that as it enters the cell membrane, it provokes production of a statin, of a factor that is going to act directly on the nuclear, on the nuclear structure, in the nucleus, on the chromosomal structure. And those are hormones like the growth hormone, the gonadotropins. They act through this, and ACTH. They act through this adenine kinase. And finally, this. So when we look at all these hormones from above coming down and look at their structures, look at their sizes, look at whether they are peptides or amines or whatever, they have a lot of things in common, because when they share receptor types, it also means they can have cross reactions. And that means high ACTH can end up with some effects on the skin, which are normally effects of beta melanocyte stimulating hormone. And that is why you find in some diseases like Addison syndrome, where you have very little cortisol in circulation, it will not be inhibiting ACTH. So you have ACTH in circulation, a lot of ACTH in circulation, and that will give you some effects of beta melanocyte stimulating hormone. Then you find hyperpigmentation of the skin. There are many, many other syndromes where you find the metabolic activity of a hormone that has increased will also affect a different function from what that hormone normally does. For example, we said TSH, or thyroid stimulating hormone, has the same structure as gonadotropins, and they act through almost similar receptors, which are reserpine receptors. And that is why you find if somebody like has hyperthyroidism or has too much TSH in circulation, it will also affect their gonad activity, what should have been affected by gonadotropins. And so you might find somebody who's supposed to get regular menses will have disturbed menses because they either have hyperthyroidism or they have hypothyroidism. You'll also find sometimes if you have ovarian issues that also are related to very high gonadotropins or very low gonadotropins, they will also affect the thyroid effect on cell membranes and therefore affect entry of glucose into cells and metabolism of glucose. And you might find that type of abnormality may be related to obesity or other abnormalities of the fat metabolism. So that many of these reactions we are going to see when we talk about disorders of or pathophysiology of different organ systems, we find hormone interactions are very important. We have also said some of the organs actually produce neurotransmitters, like adrenal medulla produces catecholamines. So when there's abnormality of too much catecholamines produced, they will go and affect receptors on the small blood vessels, the alpha and beta receptors on the small blood vessels, and they will increase blood pressure. So you get hypertension simply because there is a disorder of adrenal medulla. Probably the adrenal medulla has overgrown, has an adenoma, what we call a pheochromocytoma. So that pheochromocytoma will have a drastic effect on blood pressure, will give very high blood pressure. And this is because the neurotransmitter is the same as the catecholamine produced as a hormone. And we have many such examples of interactions between the different systems. So that is why you need to know the relationship between all these glands. You need to observe that hierarchy of hormones. I've told you that high up there, we have small molecules. We have bases. We have simple amino acids, like you have melatonin, dopamine, and then you come down and you find we'll even bring in other neurotransmitters in the brain, like 5-HT or serotonin or GABA, that is gamma aminobutyric acid. There'll be neurotransmitters or inhibitors in the brain and in GIT, and all these will have some effect on endocrine system. Then I told you now we come to hypothalamus, and that one mainly has medium-sized peptides, either 10 amino acid length peptide or 14 amino acids like somatostatin, or 45 amino acids like ACTH and others. And then from there, you find posterior pituitary also has got hormones that are like hypothalamus. They are decapeptides. Then after that, we have now anterior pituitary, which are the polypeptides of about 192 amino acids, and about 218 for the ones that have alpha and beta subunits. And they look very much like pancreatic hormones, especially insulin. So look at hierarchy. There's distribution of endocrine glands and hierarchy of the different endocrine glands, from hypothalamus, anterior pituitary, thyroid, adrenal cortex, pancreatic hormones, adrenal hormones, and then finally the gonads. Before we come to other organs that are non-endocrine, but are important in endocrine function, and those are mainly the kidney, the skin, the lungs, and the heart. Lungs have some action on angiotensin 1 to angiotensin 2. That is in changing angiotensin. Sorry, 1 minute. I'm sorry, my voice needed a little break, but not long. So I wanted to go and look at this, the flow of these hormones. Look at the way I've told you, from top to bottom, these organs. And in between now, you remember there was the pancreas that is next to the stomach. You must also look at the stomach in endocrine system. The stomach and intestines themselves produce many factors that go into circulation and affect endocrine function. And this is mainly what we saw last time. They produce peptides like secretin, they produce the Y peptides and other substances that actually go back the hypothalamus and affect the hunger and thirst centers, so that they are involved in regulation of feeding, drinking, and osmolality. So this is now a summary of what we have been talking about, that we have the different chemical categories of hormones, and most hormones are actually polypeptides or medium-sized peptides. We have already seen that. With polypeptides, you also have the glycopeptides, the glycoproteins. That is peptides that have a glycomoiety on them, mainly thyrotropin, thyroid stimulating hormone, and gonadotropins. And we find even in histology, when you look at an anterior pituitary, it will have some cells that stain acidophilic. They stain red or pink. These are the cells that produce peptides. These are somatostatins for growth hormone. These are somatotropes. Somatotropes are the cells that produce growth hormone. We have corticotropes, that are the cells that produce ACTH, or corticotropin, and the cells that produce prolactin, which are lactotropes. These three types of cells in red. The only thing you must remember about ACTH, a little ACTH is glycosylated. So you see a bit of blue paint, a little bit of blue staining in the corticotropes. But we mainly take it that they are acidophilic. What is important about this? Sometimes you have some tumors, some adenomas of anterior pituitary that only affect the acid-producing cells, the acidotropes. So that syndrome of acidotrope adenomas in the anterior pituitary will affect growth hormone, prolactin, and corticotropin. So for example, there will be increased size of the breasts, gynecomastia, and sometimes even production and unnatural production of milk, which is galactorrhea. And this will be probably common with acidophilic tumors. In ladies, it will also, of course, interfere with the menstrual cycle. Now, the others, the glycoproteins, are produced in blue staining cells, basophilic cells when you stain. And these ones we have already said are the ones that produce gonadotropins, they're gonadotropes. The cells are gonadotropes, and thyrotropes, they produce TSH. And those are the categories of chemical hormones in anterior pituitary. The polypeptides and the glycopeptides. Remember, they also have similar hormones in other areas. That is, the hormones that are produced by the parathormone, that is the parathyroid gland, that is a parathormone, the calcitonin and catecalcitonin. These are also polypeptides, although they are not as long as the pituitary peptides we are talking about and the pancreatic peptides. And as we go down, we also find pancreatic peptides are also like the polypeptides. That is insulin, glucagon, and somatostatins. And then there's a whole group or category of hormones that we look across the whole body. But at the end of the whole discussion, we'll probably talk about other medium-sized peptides, These are peptides that are produced by other systems other than the systems you have already talked about, other than the three main axes we'll be talking about, where the three main axes we'll be talking about are hypothalamo, hypophysio, adrenocortical axis. Hypophysio means pituitary. Hypophysis is pituitary. Anterior pituitary is called the adenohypophysis, and posterior pituitary is called the neurohypophysis. So we can talk about an axis from hypothalamus through anterior pituitary to adrenal cortex. That is called hypothalamo hypophysio adrenocortical axis. It mainly produces steroids at the bottom of it, especially cortisol. Then the other axis is hypothalamo hypophysio thyroid axis. That one produces the thyroxines and regulates the thyroxines. And the third axis is hypothalamo hypophysio gonadal axis. This one ends up producing hormones that affect the gonadal system, the steroids or gonadosteroids. So after we have finished those three systems through the three axes of hypothalamus, pituitary, and lower parts, as we said, we shall talk about gastrointestinal hormones, then we'll talk about hormones of the pancreas, and we'll talk about now the adrenal gland, adrenal medulla, adrenal cortex, and finally the gonads. After that, now we have other hormones. Among them, there's the local hormones. There is the lipid hormones other than steroids, and that is mainly vitamin D's and prostaglandins and procyclins. And then after all that, we have something we shall call other peptide hormones. Other peptide hormones are hormones that are not in any of the axes we talked about. And these ones include peptides that are produced by organs that are not endocrine organs. That is, there are peptides produced by the kidney, like erythropoietin, hormones produced through the lungs, like angiotensin and other substances that have got effect on lung function. We'll talk about some of them later. And we have talked about the atrionatriutic hormone. And we'll talk about angiotensin, which is also renal-related but acts on adrenal cortex. So that way you'll be able to cover all hormones. We'll also talk about the local hormones, mainly autocoids in plants, histamines, 5-HT or serotonin, and prostacyclins. And these are the categories of hormones that you need to know. And you need to know their interactions and their origin. How does the body get them? How are they metabolized? How are they lost? And what are the effects of deficiencies and excesses? So now I leave you to go and read the details of all of them, the polypeptides and protein hormones. And these are normally the large polypeptides. Best examples being growth hormone, prolactin, and insulin. Those three, you should know their features so that you can compare when you talk about other proteins. And then you talk about the glycoproteins, and we've talked about gonadotropins, FSH, LH, both male FSH and female FSH. And we have also talked about TSH, or thyroid stimulating hormone. Glycosylation increases their half-life because it covers their receptor sites, so they are not easily metabolized. And it facilitates transport in solubility, especially because we are talking about aqueous medium, we are talking about plasma. We've talked about a lot about simple amines, and these simple amines are like the hormones of the pineal body, that is melatonin, the inhibitor of in hypothalamus, and that is dopamine, and then all the other hormones that are produced by the thyroid, produced by adrenal cortex, produced by adrenal medulla. All these are simple amines. And most of them will be basophilic, will be from basophilic cells. And then a very big chapter will be steroid hormones. And it's good to look at all the characteristics of steroids, because steroids are essential in the body because of two things. One, they are so widespread in their activity. In fact, it is said there are no tissues in the body without steroid receptors. This could also be true of thyroid receptors, that we have thyroid receptors in the tissues. But in many of those receptors, thyroxine does not necessarily have activity, like in bones and other areas. But what we find is that for steroids, everything has receptors of steroids. It used to be said hair follicles don't, but it is now known they do. And in fact, a lot of hair follicle activity depends on actions of androsterones or androids, mainly 5-HT, 5-hydrotestosterone. So actually, we find steroids are very widespread. They have two major activities when it comes to homeostasis. That is, they are very important in the body adapting, changing. When changes come, it is the steroids that usually have an effect of bringing the body back to normal. When temperatures go very low, even if thyroxine is going to cause the temperatures to go high, it is the steroids that the first action. And we remember catecholamines are also very important in all the emergency reactions of the body. So that is why steroid hormones are important. They are lipid hormones, and they're mainly from cholesterol. And they are related to vitamin D, which is also a steroid. Only it's the box number 3. On the structure is not cyclic, not complete. That is, the C-ring is not closed. And you better go and look at the actual structure of vitamin D, compare with that of the normal steroid, like cortisol. Now, steroids require glucuronide conjugation for excretion through the kidney, because as you can see, steroids being lipids will only be excreted in lipid medium, it will not be transported or excreted in plasma, which is water medium. So it has to be, they have to be conjugated in the liver by, you'll find out the enzyme that is important. No, let's finish. Let's come and finish here. So hormone solubility and transport medium, that's what I was saying. For many of the peptide hormones, there's no problem because they're water soluble. But for lipids, they are lipid soluble, so they have to be conjugated. So water soluble hormones circulate freely, that is unbound in plasma. They are continually available for degradation, so that a lot of times they are lost because they are water soluble and they will be metabolized as they move along in the system. So generally they have a short half-life of 1 to 30 minutes. Most of them will have a half-life of 20 to 30 minutes. That is like the anterior pituitary hormones, the growth hormone, the prolactin, and others. Insulin will only have a half-life of 10 to 15 minutes. These others about 20 minutes. But you find when they are glycosylated, like gonadotropins and TSH, their half-life goes to 30 minutes or 40 minutes. So glycosylation increases half-life. So for lipid-soluble hormones, we've already said, to be excreted, they need to be glycosylated. However, they are mainly unbound. They are 50% bound, 50% unbound, and they can enter target cells much more easily and initiate other hormone action that is permissive. Because the cell membrane, you remember, is partial to lipid substances. So they tend to enter into cells a little bit more easily than the others. So that look at all that and look at the mechanism of hormone release, our hormones released from their cells, from where they are So I don't know what's happened to the system, fine. But I want you to go and now revise all that, look at all those slides, look at the mechanisms of hormone release. What are the factors that control synthesis and release of hormones? What regulates levels of hormones in blood? And how do we detect levels of blood in excretion? So we'll do that tomorrow from 11 o'clock. Otherwise, for now, we say that's okay. You go and now look at the slides. A lot of these we have already discussed, looking at hypothalamus, anterior pituitary, and even going right down to the thyroid. Look at the synthesis of thyroid hormones. And look at how the synthesis and release of thyroxine is regulated. And this diagram will help you to show how thyroxine is synthesized using a skeleton frame, a framework that is like a carpenter's desk, a framework that is called the thyroglobulin. And it is the thyroglobulin inside the colloidal cells of the thyroid. This is where the tyrosine molecules are combined with iodines, 1 iodine, 2 iodines, and then 4 iodines. So that we move from tyrosine to 1 iodotyrosine to 2 diiodotyrosine to 3,5-triiodotyrosine or TIT, and then the 2 diiodotyrosines come together to make a tetraiodotyrosine or T4. And we say T4 is the one we refer to as thyroxine is the main one in storage, it's the main one in circulation. But when it comes to bioactivity, we have to remove one iodine and make it T3. We make it triiodothyronine for it to bind to receptors. So the receptors are actually receptors of T3, not receptors of T4. T4 is storage and circulation. So I will allow you to unmute yourself if you have a comment, a question, or anything else. Otherwise, I'll end the class in 2 minutes, because that is the end. And I want you to read all that up to thyroxine, but look at thyroxine synthesis, release, and actions before we move on. Thank you. And you have all the notes, so you have no excuse. You come to class already having read. And look at your textbooks, also Google. Endocrine and reproduction systems are very good because you have a lot of notes in the Google, and that is online, and you can read as much as you wish. They are easy to understand. And what I'm trying to do is to just give you the principles of hormone action, the principles of endocrine system. So when you read, you can understand, and you can understand the interactions that we talk about in endocrine system. Every hormone has some effect on other hormones' activity, especially because they all use common molecules in the body, common intermediates in the body, and therefore there's a lot of interaction. In their stimulus response mechanisms, they share a lot with the neural system, so that we have a lot to do with between the neurophysiology and the endocrine physiology, especially when you talk about brain and nerve action. Thank you. Any comment? So if there is no comments, I'm going to call it off. We meet tomorrow at 11. You can unmute yourself here.